Hey everybody, I'm Chili. Welcome back to Intermediate C++ Tutorial 2. Today we're doing pointers. Now, pointers have a bad reputation, but they're not super hard. They're actually pretty easy to understand and use. The problem is that they're also pretty easy to make mistakes with. You gotta be very careful. You're playing with a loaded gun here. Modern C++ deals with naked pointers a lot less. It uses some more sophisticated tools instead. And I'm going to be teaching those tools later. But you still need to know how a basic pointer works. Just for, reading other people's code, interacting with APIs. Sometimes you got to use them. So I'm going to teach them here first. Now this tutorial is going to be split into two parts. The first part is going to teach the basics of pointers, the most common operations. And then the second part is going to teach some less common operations, but they're still important to learn. And you should make note that there's going to be short homework for both part 1 and part 2. Alright, let's get this party started. We're going to go new project, and we're going to make just an empty project here. You can call it whatever the fuck you want. I'm calling mine Poindexter. There we go. So yeah, we're going to be working in console applications for the time being, for a while here. I know in the introduction to intermediate video I said we do graphics, but then we're going to do console. Yeah, so whatever. Add new item. We need a source file. We'll just call it source, because we're lazy like that. And so for console applications, you need an entry point, and we just call that main. We don't have to take any parameters. There are different kinds of main signatures you can have. This is the simplest one. Return 0. There we go. So I'm going to type out some code here, and you guys are going to watch me type, and I want you guys to try to figure out what's going to happen here. So first we'll do some int n is equal to 5 action. Then we're going to do something a little bit, we're going to switch it up a little bit. Int star p, and then we're going to do p is equal to ampersand n, and then we're going to do star p is equal to star p plus, and we'll say 60, just a random number, 64, that should be good. That should be good. And now I'm going to build this guy, and I'm going to put a breakpoint right here. And I want you guys to guess what the hell is going to happen with these variables, n and p. So we got our n, it's got some weird number. We got p, it's also got weird numbers in it. Let's step over. So we set n to 5, that's great. We set p is equal to ampersand n, and p has changed to some funky hexadecimal. This is representing this in hexadecimal, by the way. This one's being represented in decimal. And now we do star p is equal to star p plus 64. What is going to happen? Well, I guess maybe p is going to change, right? And psych, p didn't change, but n did change. It's a magic number. What the hell's going on here? Well, let's go over it line by line. The first line, pretty simple. You guys should know this. Declare a variable n. Compiler makes some space for it and initializes it to the value 5. Now the second line looks similar. It looks like we're declaring a variable, and we are declaring a variable, but this star here means we're declaring a special variable, a pointer. So if you want to declare a pointer, you put a type name, a star. So why the type name? Well, a pointer points to some kind of variable, some kind of type. So you've got to tell it, you want a pointer to int, or you want a pointer to float, or you want a pointer to poo. So you put a type name, you put a star, that's how you declare a pointer. Great. Next line, what is this bullshit? Well, you've got a pointer, but when you initialize it, it ain't pointing to shit. It's just pointing to somewhere random. You want to make it point to your variable in memory, and this is how you do this. This is how you make a pointer point to a variable. You go the pointer name, assigned, and then ampersand n. This ampersand is called the address of operator. I'll talk a little bit about that later. But yeah, this is how you make a pointer point to some variable. And then here we are accessing the target of the pointer. So when you want to access the target, you put a star in front. When you want to change what the pointer is pointing to, just naked pointer name. But if you want to get at what the pointer is pointing to, we call this dereferencing the pointer. you put a star in front. That's the dereferencing operator. So what we're saying is, get me the thing that P is pointing to, and that'll get us a 5. Now add 64 to that. We're at 69. Now store that into the variable that P is pointing to, and that'll store that into N, hence N changed to 69. Mission accomplished. All right, let's try some other stuff. What if we tried to assign an integer value to P? What is that going to do? Well, the compiler is going to complain because cannot be assigned to entity of type int pointer, right? These types are not compatible. A pointer variable holds pointer types, but this is just a standard integer. It's not a pointer. So you can't assign an integer to a pointer. Doesn't make no goddamn sense. What else? Well, let's create a variable float f, and we'll try to make our pointer p point to f. Can't do it because, again, the types aren't compatible. They're both pointers. You can see float star and int star, but float pointer is not compatible with int pointer. You can't make a pointer to int point to a float variable. Again, it doesn't make no goddamn sense. Now, there's one special thing that you can make p point to, and that is a special value called null pointer. And what that value says is this pointer is not being used. It ain't pointing to shit right now. And it's we use this very often to indicate when a pointer isn't pointing to something. And we'll be seeing more of null pointer a little later. Another thing you can do is you can assign one pointer to another pointer if their types are compatible. So here we're making p point to the variable n, and then here we've made a pointer q, and we're going to make it point to the same thing that p is pointing to. So we assign p to q, and now they're both pointing to n. All right, now let's take a look at how this shit goes down in terms of, memory layout and actual CPU operations. So again, the first thing the compiler does when it's going to compile a function is going to take a look at the local member variables, and it's going to give you space for them in memory. Now, we've got 3 local variables here, n, p, and q, and I hear you saying, well, Chili, p and q are pointers, they're not variables. But a pointer is just a special kind of variable. It's a variable like any other, except that it has a very special role in that the meaning of the variable is to point to a place in memory. Now, the other thing I want you to notice is the size of our pointers, right? They're 4 bytes, the same as an integer. And this is the case if we are compiling a 32-bit exe. If we were 64 bits, these would be 8 bytes, right? So this size of the pointer actually depends on what mode you're compiling in. Now, the first line of code, this is simple. We just store 5 into the, integer at 1000. The second line of code, here's where things get interesting. So the first part of this expression here is the ampersand n, which is this ampersand, again, like I said, is called the address of operator. Address of. And what it does is it tells the compiler, calculate the address number of the thing to my right. So what we're doing here is we're telling the compiler, calculate the address of n. And the compiler says, well, n is just a variable. I jammed it at 1000. So the address of n is going to be 1000. So the compiler goes, okay, well, 1000, and we're going to jam that into p. Now, p is a pointer, but a pointer is really just, in 32-bit mode, it's really just the same thing as an int. It's an integer number that indicates an address in memory. So it's just going to say, well, jam the address 1000 into the integer type at 1004. And that's how we store our pointer, and that's going to go into here. The hexadecimal for that is apparently 03E8. So great. Now our pointer is storing the address of the variable n. So let's just draw a little picture here. That means that this pointer is now pointing to n. Great. What's next? Well, yeah, so we get the address, we assign it to p. Now we want to do p is equal to p plus 64. So what do we do here? First things first, we've got to load the value of the thing that p points to. So first we need to know the address of the thing that p points to. So what the compiler does is it says, okay, well, I want you to load the address stored in p into a register. So we're going to do the int at 1004. So that's the value, the pointer value, the address stored in p. And let's load that address into register B. So that's going to be loaded into here. And this guy is going to have, you know, a big old 1000 stored in him now. So now we have that address in B. Now we want to get the value at that address, right? Because we're dereferencing the pointer. So we want the actual targeted value. So then we do, well, let's store that value into A. So we do the int at B, right? Because we got the address of the target is in B. So we take the int at B and let's store that into A. And so what that'll do is that'll say, well, B is 1000. So we look at address 1000 and we take this stuff and we jam it into A. So now A has a big old 5 in it. Now we got to add 64 to that. So what do? Well, we take A, we add 64, and let's just store that back into A. And if we do that, A is now going to have a big old 69 in there. Big old 69. So now we've calculated this expression here. Well, all that's left is to store that back into the target of P. And as an optimization, the compiler might say, well, I mean, we've already loaded the target's address into B, so we don't have to do that again. Let's just use that. And so we'll store A into int at address pointed to by B. And that will say, well, B is 1000, so we're going to store A into address 1000. And that should look something like this. Final line is very simple. We're just going to load the address stored in P, the number stored in P, and then store that into Q. And that's going to look something like this, and it's going to load from here and then store into here. Pretty simple. And when you do that, you see now they have the same value, which means they both point to the same place in memory. All right, so great. We can make a pointer P, we can make it point to N, and then we can do star P, and that basically acts like we're accessing N directly. This is basically the same thing now as if we just typed N and N in here. It would be the same effect. And so you might be asking me, well, Chili, then why don't I just type N in directly and forget all this pointer bullshit? I don't really see the point. And the point. But this is obviously just a simple example. There is no reason to use pointers in this situation. And it might seem obvious, but I just want to make it clear that you shouldn't be using pointers if you don't have to use pointers. In this situation, that was just a dumb example. I would never use pointers in that situation. Let's look at a situation where you would use pointers. All right, so let's say we got a situation here. We want to create a function that will swap the values of two variables. So the idea is that we pass in M and N, and the values now, M will, after we call swap, M will be 5, N will be 7. But you guys should know this, because I've covered it already. But this isn't going to work, is it? Like if we step over here, M is 7, N is 5, swap should swap them, but it don't swap them. And if you guys don't understand why that is, you really got to go back and watch my beginner series. Basically what this is doing is it's loading the value of M, the value of N, it's passing them to this function here. So 7 is being stored in A, 5 is being stored in B, then A and B get swapped. But that doesn't have any effect on the original M and N because they only had copies of their values passed in to this function. Now, what if we change this function a little bit, though? What if instead of taking integer values, it took pointers to integer? So now we would pass the function pointers to the things it would want to swap, and it will swap them via pointer remote control, right? This seems like it'll work. And the only question now is, what do we pass to the swap function? It takes pointers. Well, pointers, the pointer value type is just the address. So all we got to do is pass it the address of M and the address of N, and this will calculate these addresses. It will pass the address values to the function, and those will be stored in the pointer variables, and then those pointer variables will be used to access those addresses in memory, which correspond to our variables M and N. And now if we run this bullshit, we should see our shit being swapped. 7, 5, and voila, 5, 7. We swapped our shit. Now you might be saying, Chili, I'm feeling a little bit of deja vu here. This looks familiar. And it probably should, because this is the exact same example I used to teach references. And indeed, references and pointers are very similar. The main functional difference between them is that pointers can be retargeted, but references are stuck pointing to a single thing. This one fundamental difference accounts for all the differences we see between pointers and references. So because a reference cannot be retargeted, you must initialize it when you create the reference, because after you create it, you can't target it to something. Whereas with a pointer, you can declare a pointer without making it point to something, and you can retarget a pointer at any time you like. But because of this ability to retarget a pointer, pointers need extra syntax, right? You have to be able to distinguish between retargeting a pointer and accessing a target. Whereas with a reference, once you capture the reference, there is no retargeting, so you can just make it act like another variable. The syntax is the same as any other variable. So assigning one thing to a reference will just be the same as assigning it to the variable that reference is targeting. Whereas with a pointer, you have to distinguish between changing the pointer and changing the target. Now you might be saying, well, I guess pointers are just a more powerful reference. Why don't I just use pointers for everything? But that's actually stupid. Take a look at the example up here we don't actually need to retarget these pointers. They are going to be initialized at the beginning of the function, and they're never going to be retargeted. So there's actually no point in using pointers here. If we replace them now with references, we get much cleaner syntax, and there is less chance of fucking up, because we can't have the pointers point to something invalid. We can't mess them up by accident. So the rules are, always prefer using variables directly over using a pointer or a reference, and always prefer using references over using pointers. But sometimes you gotta use a pointer. Specifically, if you need to retarget, then you need to use a pointer, because references cannot be retargeted. Now, you can make pointers to point to custom types like classes, and it works the same as pointing to a basic type like an integer. You just put the address of operator there, you make your pointer point to that thing. So now pfoo is pointing to my foo. You can also make pointers point to members of objects. So here I create an integer pointer and I make it point to the Baz member. So I go myfoo.baz and then I get the address of that. That'll calculate the address of the Baz member in myfoo, and this will point to that member. And you can do the same thing, but you can use the pointer. So you can use a pointer to an object to get, for example, a pointer of the member. So here we dereference pfoo. That gets us myfoo. Then we got to put these parentheses around it because we want to say that the dot operator is working on the dereferenced object. If we remove the parentheses, it's going to try to apply the dot operator to the pointer, but that's not what we want to do. We want to apply the dot operator to the object that it points to. So the first thing we got to do is dereference it. Then we can apply the dot operator, say we want to get at the phys member, and then it's going to get the address of the phys member, put that into this car pointer. So now pcar is pointing to the phys member of myfoo. Now this dereferencing plus these parentheses can be annoying to type. You have to type this if you want to dereference and get at a member. There is a shortcut in C and C++, and it looks something like this. It looks like a pointer. It's just a dash plus a greater than. And that's going to say, okay, dereference the pointer and access the member phys, and then we get the address of that whole thing. And now we don't need the parentheses, and it looks cool. You gotta admit, this looks kind of fucking cool, right? So this is generally how we use a pointer to access a member of a class. We use this operator here. Now, while we're on the topic of classes and pointers, let's tie up a loose end here. Remember when we defined our operators for the vec2 class? I told you that assignment type operators like plus equals and minus equals, they should be returning a reference to the self object like this. Do you remember how we did that? Yeah, that's right. We did star this. Now, what does that suggest to you? Well, it should suggest to you that the keyword this is actually a pointer. All non-static member functions have a special pointer variable automatically defined for them called this, and it points to the object on which the member function was called. Now, the this pointer is useful sometimes, like when you need to return a reference to yourself, or when you need to pass the address of yourself to a different function, but it can also be used to disambiguate. Like, imagine you got some dumb function. It takes in two parameters, x and y, and the idea of this function is to multiply those parameters by member variables and then return the result. The problem is if the parameters have the same name as the member variables, they're going to cover up the member variables in scope. So you're going to want to do this x times this x, but you're just going to get this x times itself in here. Now, if you use the this pointer, you can disambiguate. You can say, no, give me the x of this object and give me the y of this object, and then I'll multiply those by the local x and the local y. And there you go. Now you don't have to rename your parameters. I still recommend giving the parameters different names than the names of the member variables, but if you really don't want to, this is a way that you can get around that. And there you go. That's the this pointer. One more mystery cleared up. Now, let's say we have an array of integers and we want a pointer to point to an element of that array. Can we do that, and how? Well, I mean, if you want to access an element of an array of integers, you would go array at the index you want. So if I'm going to get element 2, that would just be array 2. But that will give me the value of that element. I want to get the address of the element, so I use the address of operator in front of that. And there you go, it works fine. Now this pointer is pointing to here. We run this code, we see we are initializing our pointer to point to element 2. That's going to change its address like this, and now the thing it's pointing to has a value of 12, which is correct. And then if we try to assign 69 in there, let's look at our array. Assign 69, and the value does change to 69. No problem. Up until this point, we have been using the star operator to dereference our pointers, but there's another way to do that. So take a look at this code. What do you think it's going to do? Well, first off, we are going to initialize our pointer to point to array element 1, so it's going to be pointing to this guy. And then here, what's this? What is this garbage here? What is this going to do? Well, this is dereferencing the pointer, but it's not dereferencing it directly. So it's not going to dereference to this location in memory. It is going to dereference it with an offset of +2. So it's going to dereference it, but it's going to dereference the memory address 2 ints over. So it's going to move over by 2 ints, and it's going to access this guy. So it's going to set the last element in the array to 69, theoretically, if I haven't completely had a brain aneurysm. So let's just take a look at our array. Element 3, what's it going to be? 69, just like Chili told you. So let's quickly take a look at this code under the microscope. We got our shit set up. Now we're on this line here. So first thing we're gonna do is we're gonna get the address of r at 1. So it's gotta calculate r at 1. Well, it knows r is 1000. So it's 1000 plus index 1 times the size of an int, which is 4. So it's gonna take that address and it's gonna store it in the int at 1016, which is our pointer. So that address is going to be 1004, right? 1004, which is whatever. I don't know what that is, and I'm not going to calculate it. So 1004, our pointer is now pointing there. Now, what it's going to do is it wants to store the value 69 into the memory location pointed to by pint offset by 2 integers. So what is it going to do? Well, first it's got to load that address and calculate the offset. So what it's going to do is it's going to first do, the int at 1016, store that into, some register. We'll just store it into B. Then we got to calculate the offset from that point. So we calculate B plus 2 times the size of an integer, which is 4. and we store that. We'll store that back into B. So 1004 plus 8 is 1012. So now B is pointing to 1012, which is correct, right? The last element of the array. And then we consummate this marriage, and we store the value 69 into the integer at memory address pointed to by B. And there you go, Bob's your uncle. So not only can we dereference the pointer directly, we can also index from the pointer location into some other location in memory relative to where the pointer is pointing. Now you might be saying, well, that's weird. Pointers actually, they seem to look a lot like arrays now. That's strange. Well, let me show you something. Let me blow your mind a little bit here. So let's say we've got this pint. It's going to be pointing to the first element of the array, element 0. And then we index 2 in. What do you think is going to happen? What's going to change? Well, let's look at our array here. And yeah, so element 2 changes. That is what you should expect. Now let me do something here. Let's get rid of this and get rid of this. So we just use the name of the array directly. We assign that to the pointer. What do you think is going to happen? Take a guess. What happens is the exact same thing. Why is that? Why do you think that is? Well, a naked pointer is just an address, and then you put the index after that to get at an element relative to that address. Well, a naked array name is also, it just evaluates to an address. It evaluates to the address of the start of the array, just like a pointer would. So in fact, arrays behave almost the same as pointers. And so this expression here is just assigning one pointer to another pointer. Let me prove my point further. We'll do star ARR is equal to 5. And if we check it, you will see, search your heart, you know it to be true, this just modified the first element of the array. So array names by themselves, arrays are basically just pointers. They're actually not pointers, but they behave like they're pointers. There's only really two main differences between working with an array and working with a pointer. Difference 1, you cannot retarget an array. So this array symbol is basically keeping track of the beginning of the array in memory. We cannot make that now point to some other part of memory. That is no good. You can't retarget an array symbol. Now the other difference has to do with the size of operator, and I haven't talked about this. This is like a function that's built into C++, and what it does is it gets you the size of the type as an integer. So for example, if I do size of pint, that will give me the size of a pointer to int, which should be 4 bytes, right? And if I run this, look at size p. When I step over, size p is equal to 4. So a pointer is 4 bytes. Watch when I change it now to 64-bit mode and run this bullshit. Now it's going to tell me a pointer is 8 bytes. Makes sense. But when you use the size of operator on an array symbol, you get a different thing that happens. It doesn't tell you the size of a pointer. It tells you the size of the entire array in bytes, which is 16, right? And int is 4. We've got 4 elements. 4 times 4 is 16. So that is the other main difference between arrays and pointers. Again, to recap, you can't retarget an array, and the size of an array will actually give you the size of the whole array, not just the size of a pointer type. So again, arrays are not the same thing as pointers, but you can see how things are all related. Things are connected. They mesh together. And that connection is going to be even stronger once I introduce strings. And that's why I want to teach all these concepts together. You know, strings and arrays and pointers, because they all kind of flow together. It's all connected, man. All right, it's homework time. For the homework for part 1, what I'm going to get you to do is create a function. Let's call it sum. And you're going to want to be able to give that function an array of ints, and it should calculate the sum of all the elements in the array. When you're done the homework, you can watch the solution video for part 1 and then proceed on to part 2 of pointers. Thanks for watching. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more C++.